So hey everybody, welcome to ARE Live. I'm Mark Tier, the founder of Black Spectacles. And today's episode features Mike Newman, who's going to review the questions and answers from our Building Systems mock exam. The questions that Mike will review will help to give you a strategy for how to study for this exam and some of the terms and topics you're going to see in this exam. And if you haven't done so, make sure that you download the mock exam in the show notes. But before we get started, if you'd like to attend our next ARE Live broadcast, visit blackspectacles.com/podcast to register. During the broadcast, you'll have a chance to ask questions and share your answers with Mike. And if you don't know Mike, he's an adjunct professor at the School of the Art Institute of Chicago. He's also the founder of Shed Studio, and he is the instructor for Black Spectacles' online AIA ARE prep curriculum. If you haven't already checked out our AIA ARE prep curriculum, head over to blackspectacles.com to watch any of the free tutorials from the courses. And today we have two very special Black Spectacles promo codes to share, so make sure you stick around until the end of today's episode. But first, let's hand it over to Mike.
We're going to dive right in. First one we're going to sort of test out. The question is, a step-down transformer has the following characteristics. It has a primary voltage of 240 volts. It has a primary current of 5 amps. It has a primary coil with twice as many turns, sort of rotations around the cores, as the secondary coil. What is the current and voltage on the secondary side of the transformer, neglecting any power losses? So first of all, every time you have a transformer, every time you transform energy from one voltage to another, there's always a little bit of power loss. That's for the purposes of the exam, for the purposes of any of this kind of stuff, would always be neglected because it just gets too specific and complicated. So the key thing to take away from this discussion is there's sort of a basic tenet to how you think about volts, amps, and watts. And the simple thing is volts times amps equals watts. So what that's referring to is, and I'm putting this into my own terminology, this is not necessarily the most technical way of describing it. If you think of volts as the energy per charge, and then amps as the flow of those charges. So it's just the easier way to kind of imagine these things. They're related to each other, but they are not the same thing. One is about the charge moving through. The other one is how robust that charge is. And then that equals watts, which is power. So the ability to do work. Now, one of the weird things about this discussion for most of us is that most of us grew up thinking of watts in relationship to light. That you think of a 100-watt bulb or a 60-watt bulb, and it's about the amount of light that comes from that. That's actually just sort of a happenstance from history. And as incandescent bulbs go away, it'll become even more and more a happenstance of history. The reason that we think of that is just because when you put more power into the light bulb, it gives us more light. And so it's just a representation of power, of the ability to do work. So watts doesn't have anything to do with lights. It's just power. Volts and amps are the way that we think about that. So we have this very straightforward, simple relationship, volts times amps equals watts. So given that, we look at our options. Option A is 10 amps at 240 volts. Option B, 5 amps at 240 volts. Option C, 5 amps at 120 volts. And option D, 10 amps at 120 volts. If we think about this, all this is really asking us is, do we understand that volts times amps equals watts? The power doesn't change. You're not changing the total power that the transformer isn't magically making more power, right? There's the same amount of power on either side of the transformer. What's being transformed is the voltage and the amps, the flow and the amount of energy per charge. So essentially, 5 times 240, which would be equal to the watts, that has to be the same. We have to have the same number out of our n choice. So if we look at 10 times 240, which would be A, well, that's going to be twice as much. It's not. That's twice as much watts. Doesn't make any sense. 5 times 240 again. Well, we haven't transformed anything, so B can't be it, because why would you have a transformer that doesn't transform anything? C, 5 at 120. We've actually cut the total watts in half if we chose C. So the actual answer would be D, 10 amps at 120. And that's simply because 10 times 120 is equal to the same thing as 5 times 240, right? You can tell the fact that the primary coil and the secondary coil, there's a 2-to-1 ratio of the coils. And that 2-to-1 ratio tells you that either, depending on whether it's the primary going to the secondary or the secondary going to the primary, that tells you that it's going to be either half the amps or double the amps, and half the volts or double the volts, right? There's other ways the coils can be dramatically different. You can go from very, very low amps to very, very high amps. But typically in a question like this, it'll be a fairly simple, straightforward one, something like that. So the simple issue here is volts times amps equals watts. That's the sort of energy that each of those charges carries. And then how many of those charges per second would be the amps. And then the total work that you get out of that, which is the watts. And this is just a description of that, right? So the transformers, the thing they can't transform the total power. What they can transform is the flow of that power and the amperage and the voltage of it. All right, let's try number 2. So question number 2, a residential client has requested that a low velocity forced air system be designed for both heating and cooling. The building is located in a location with comparable heating and cooling degree days. Which of the following statements is true for this situation? The duct system will be sized for heating mode. The duct system will be sized for cooling mode. The duct system is limited to high supplies only. The duct system is limited to low supplies only. So there's a couple of things to sort of think about when you look at a question like this. First of all, which are the things that are just kind of there to throw you off? And to me, the C and D are really there just to throw you off. I don't even really know what high supplies only and low supplies only would mean. It's not really a relevant terminology. So I would just get rid of C and D as possible answers. So then the real question is A and B. In this situation where the heating and cooling degree days are comparable, do you design the duct system for the heating mode or do you design it for the cooling mode? So first of all, degree days. This is just a way of sort of statistically understanding, like over a span of a number of years, you count the times that the numbers of degrees and the number of hours of days that that area is needs to be heated, and then that same question about how many times and how many hours over the span of a couple of years, averaged out for a year, that area needs to be cooled, right? And so you could find out very quickly. This is sort of, you can look this up, and you could find out if we go to northern Canada, you're going to find that there's not a huge number of cooling days, but there's going to be an awful lot of heating days. So you're going to get those degree days. So you would know that what you're designing for is the heating system. The cooling system you might need for a month or so, and that's fine. You design a little system and it'll work, but you'd be designing for heating. Well, if we looked at Tucson or some other place that's very clearly very, very warm, if I look up in the charts, I'd find that the cooling days are going to be off the charts, but the heating days are going to be much less important. Actually, Tucson's probably a bad example because it gets cold at night. How about Florida? So this is a way of sort of thinking about, sort of in an abstract way, which do you need to design for? Do you design for the cooling load or do you design for the heating load? Well, what this is telling us, this question is telling us, is that it's roughly equal. So how do we design the ductwork? Okay, so degree days, that's what that's about. Now we're saying, all right, what's going on if they're roughly similar? How do we think about this? So you can see I've got a little sketch off to the side here. And that little sketch is talking about in the summertime, I'm saying, let's say the sort of ambient temperature in the room is roughly about 75 degrees. Okay, I'm going to be bringing in air that's, say, 60 degrees. It might be as low as 55 degrees, something like that, but it's not going to be much lower than that. So the delta, the difference between the ambient air and the air that we're supplying, the conditioned air that we're supplying, is somewhere 15, maybe 20 degrees. Now you might ask, well, why only 55 or 60 degree air? Like, why not supply in 30 degree air or 42 degree air? Think about that for a second. Now, imagine you're the one in your office sitting right below the register, right? And that 30-degree air is dumping right onto your desk as it starts to mix into the rest of the space. You would be complaining immediately, right? It's one of those things, it's totally about comfort. It's about the human body. The human body just doesn't like to have cold air blowing on it. It would drive you a little crazy. Whereas if we look over on the winter side, if the ambient temperature is, say, roughly 68 degrees, the air that we're supplying in there might be 100, 110, 120, but it's going to have a much bigger delta. So we're going to have a delta anywhere from 40 to 60, somewhere in that range, maybe even higher. So the air that we're supplying has, there's more difference in the air temperature in the heating than the ambient temperature than there is in the cooling compared to the ambient temperature. So the difference is really dramatically different. Therefore, in order to make 1 degree difference, in order to bring the 75 down to 74, I need more CFM in cooling air than the similar example of bringing the 68 up to 69. I can use less CFM because I have more of a delta. So hopefully that makes sense. It's solely about comfort. Our bodies don't mind having a delta of 40 or 50 of hot air blowing on us, but it does mind if we have a delta that big of cold air blowing on us. So because of that, in that comparable degree days for cooling and for heating, we would absolutely be designing with the cooling in mind. So the heating has to kind of suffer through going through much bigger ducts than it really needs to because it'll work. But the cooling, you have to design to make that work because you have to get more air through that system. So kind of a long story, but simple idea. It's really all about comfort and how people react to it. And then that delta difference that you're able to use in the difference between cooling and heating. Like I said, if you're talking about, Edmonton or Tampa, Florida, where the extremes are so clear, it wouldn't be a question. You would just be designing for the heating. In Northern Canada, you would just be designing for the cooling, and that would work fine. It's just in this context where we're saying those degree days are equal, so there's nothing else driving that decision. It's only a decision based on what's the most efficient. Okay, let's look at number 3. So number 3 is kind of a funny one because this is both the simplest question and the one that I'm probably going to take the longest on, just to give a little bit of background. So question number 3 is, what does the common abbreviation DX stand for? We have a couple of examples here: double expansion, direct exit, double expulsion, direct expansion. I kind of like some of those. I like direct exit. That's kind of a nice one. Double expulsion sounds like maybe a good Jean-Claude Van Damme film or something. Like, I think it has some real possibilities, but it's not a potential answer for us. Direct expansion is what DX stands for. So let's back up for a second and talk about what we're really talking about here. Okay, for HVAC systems in big commercial structures, the way that the easiest way to sort of imagine this is to think of it as 4 loops. So if you think about, there's one loop, the one right in the middle there with the 2 little boxes at the top and the bottom. The one loop is the refrigerant loop. So what's the refrigerant loop doing? Think about it as one set of material going through one set of pipes, and it's on one side, and then it's on the other side. And then it goes back to the other first side, and it goes back to the second side. So it's one loop. The only thing that's changing is we're changing the pressure of the refrigerant in that system. So we have a compressor and we have an expander. And if you think about that for a second, you probably already understand that when we use a compressor, so it's the same material, nothing else has changed. All we've done is change the pressure, and we've made it much higher pressure. The temperature of that material goes up because there's a direct relationship between pressure and temperature of any one given material. The reason we use refrigerants is because they happen to be really useful. The temperatures that this all works at are incredibly useful. They just work out to be temperatures that are very helpful. So other materials will do the same thing. They just don't do it in ways that are as easy for us to manipulate. So the refrigerant, the whole point of the refrigerant is that it does this at this really easy set of temperatures. So we have this loop. We compress the refrigerant. It gets very, very hot because it's all very dense and tight. Think of yourselves like going into you have 100 people and you go into a small room. You're going to get really hot, right? It's that density, right? It's going to make everybody really hot. Then you take that same 100 people and you go into a much, much larger room. Everybody cools down, right? Everything gets sort of cool and easy. So we compress it. The refrigerant gets very hot. We then let it go over to the expander. And like one of those little spray things you use, spray air things that you use to clean off your computer keys, right? You ever do that, right? When you spray it off, it gets really cold. Well, the same thing is happening in the expander, in the refrigerant. We let it free from its intense pressure, and now it cools way down. So the only thing that's changed is the pressure on the refrigerant, but that has changed the temperature of that refrigerant. This was a kind of useful and key sort of understanding of how we can start thinking about air conditioning, because heating is relatively straightforward. You burn something, it gets hot. You take that heat and you blow it around, move it around some way, right? But air conditioning is really tricky because you can't just make cool, right? Start thinking about it for a second. It's like, how would I make cooling? Well, the way that I make cooling is by removing heat. So I'm actually moving heat around when we talk about air conditioning, cooling systems. So because this refrigerant has this ability within this one single loop, I now have one side of the loop that I can then relate that refrigerant to, say, a big barrel of water. And that hot side of the refrigerant is going to be in that big barrel of water, and it's going to make that barrel of water hot. It's going to give a bunch of its heat to the water. Well, I can then take that water and take it somewhere else and expel that heat. Maybe a cooling tower on a roof, maybe somewhere out back, something like there's some way that I'm going to be able to take that heat and move it somewhere else and expel it out to the world, out to the sky. The other side, I have a barrel of water, but it's cool on the other side. So essentially what I'm doing is, because the refrigerant is cooler than the water on the cooling side, it's accepting the heat from that water into the refrigerant. So that when that refrigerant on the cool side is accepting that heat, it then goes to the compressor, it gets hot, it gives that heat that it just accepted to the water on the hot side. I can then expel that heat. So effectively what I've done is I've moved heat from the pool of water on the cool side. I've taken heat from there and I've moved it over to the water on the hot side, and I can get rid of it. So I have a heat rejection loop going off to the one side, and I have a chilled water loop going off to the other side. So I've essentially, by pulling the heat out of the water, I've made the water chilled. I've chilled the water because I've removed the heat, some of it, some percentage of it. So the refrigerant loop is right in the middle of that. I have the heat rejection loop on the one side. Sorry, going backwards here. And the chilled water loop on the other side. And then I can take that chilled water and I can take it anywhere in the building, right? Water is very easy to move around. I have pipes. It's expensive to do the pipes, right? It's not a cheap process, but it's very easy. It's very small. I can move a lot of temperature around quickly and easily. So I can place that water anywhere in the building. And then I have the fourth loop, which is the air side loop. So I have an air handling unit somewhere. I may have many of them. I might have one on every floor. I might have one every 2,000 square feet. I might have one every, like, however you're lining up the building, I'm going to have at least one air side loop. So I have the air loop that is taking the cold water, the chilled water, using that in my coil and blowing air across it. And then that air that we blow across it becomes the supply air, goes into the supply duct, moves out into the space, goes through the branches of the supply ducts, goes into the actual space where the people are occupying it, it gets used, breathed in and lived in and all of that, eventually finds its way back into the return system, comes back to the air handling unit, gets reconditioned and blows out again. So that's a whole internal by itself loop, that air loop, blowing air out and we're letting it return back. There's a few little complications of bringing some outside air and some other stuff, but essentially that's one sort of standalone loop. So I have 4 loops to make this system work. Almost all air conditioning systems are based on this basic idea. It's all based on this idea of the refrigerant loop. There's a few examples where that's not true, maybe 5-8% or something of the examples out there, but almost all of the examples you'll run across will be based on this basic idea. The sort of one caveat there is you don't always have all 4 loops. So I'm going to look at one example. Actually, I'm going to look at 2 examples, but we're going to look at one example first. So this is a little kind of wacky sketch of a kind of classic example. So if you think of this down at the bottom there, I have the chiller, right? You've probably heard of the term the chiller. The chiller essentially is I have a refrigerant loop, and I have a barrel of water on one side and a barrel of water on the other side. So I have a hot side and I have a cool side, the chilled side. So I have that compressor and I have the expander, and it compresses the refrigerant and makes it hot. I give that heat to the hot barrel. It makes the water hotter. I then take that water, in this case, up to a cooling tower up on the roof. That's what that little thing on the side there is representing. So the water goes up. In this particular case, the water goes up and sprays down, and through evaporative cooling and through just kind of the sheer nature of spraying water, you'll get rid of a lot of the heat from that water out to the environment. I then recollect that water. It goes back down into the barrel to be heated up again by the hot refrigerant. The other side, I'm creating the chilled water loop. I have the chilled water on the other side. I make this big loop. I take that loop anywhere in the building. I put it in front of the fan and the air handling unit. I can then condition that air for the air side loop. So you've got all 4 loops represented in this. This is kind of a classic sort of, it's a 1950s building. Yeah, that's what it looks like right there, right? I've got the chiller in the basement. I've got the cooling tower on the roof. Those things last forever. They're pretty efficient and very flexible because I can always change the pipes around and change the whole systems. The air systems are located wherever they need to be and not where they don't need to be. So that's a classic sort of basic system, shows all four loops in action. But then let's look at one other example. This would be a DX example. So this is direct expansion. What this is saying is this is a rooftop unit. Again, kind of a crappy little sketch, but you get the idea, I hope. This is a rooftop unit. There's lots of different DX versions, but what this one does is there is no chilled water loop. So this one is saying we're going straight from the refrigerant. When we make the cool side of the refrigerant, instead of making cool water and then taking that wherever we need to go, we just take the refrigerant and put that in the coil right in front of the fan coil, the air handling units, the fan coil unit. So the refrigerant itself is actually interacting through the coil with the fan. So it's direct. It's a direct expansion. If you think of the term direct, it's probably the easiest way. It's direct from the refrigerant to the air side loop. We skip the chilled water loop altogether. There are certain advantages to this, and there are certain disadvantages to this. This particular example, where I have a rooftop unit, this is a classic example for kind of multi-tenant buildings. Maybe I have a 3-story loft building that we're putting in a bunch of different tenants in, and who knows how long they're going to be there, right? They're going to be there 3 years, they're going to be there 6 years, they're going to be like, you're not doing the headquarters for General Motors or something. Or Google or something like that, right? It's sort of, there's a transient aspect to it. Well, this is sort of a perfect little system, right? Because I can take this straight off the shelf. It's a whole system all in one box. Take a crane, I put it up on the roof. The whole thing is there. It's got the heat rejection system going straight from the refrigerant into the heat rejection. It's got the coil with the refrigerant and the fan, the fan with the coil creating its own air handling unit right there up on the roof. The only thing I need is to have a duct that leaves from that system and goes down through the roof into the space that I'm trying to heat or cool. So it's a very simple system that I can easily put up on the roof. Direct expansion, no chilled water. That's all it's referring to. This is one example of this. And just since I brought this one example up, think about why this would be a great system and why it would be a terrible system. So while you're thinking about that, would you like to live on the roof? Probably not, right? Depending on where you live. It's got to deal with snow, sleet, rain, UV rays, sun, right? So this system, compared to that chiller in the basement that was built in the 50s, this system is going to be replaced every 10 years, every 12 years, something like that. It's going to have a very limited lifespan because it's just a terrible place to be up on the roof. You get all the worst of everything. But if that's appropriate to the type of tenants that you have, if that kind of turnover makes sense, then that's fine. The other big problem with this as a system is the way to make this work is I put a giant hole in my roof, right? Because I have to get the air from that box down into the building. So instead of using those nice small water pipes with the chilled water in them moving around the building, I'm actually moving around with these huge big ducts, and it takes up square footage. I have big holes in the roof. I have all these things that are sort of problematic, right, with leaks and all those kinds of problems. So the right system for the right project. DX tends to be these kind of are more typically used for projects that are more transient. I think it's probably the best way to say that. So that things are going to move in and out. That's probably going to be a sort of logical choice. Other systems that are more like kind of institutional or something like that are probably going to be more associated with like chilled water systems, chillers, where they have much longer lifespans, more centralized control over these pieces. If you imagine I have these rooftop DX units, I'm going to have to place a whole bunch of them up on the roof to deal with all the different tenant spaces. So everything's decentralized, which means the maintenance is decentralized, which means, all of those kinds of things, which makes sense if I have individual tenants. It doesn't make so much sense if it's a college campus or something where it would make sense to have that be as centralized as possible, right? So the right system for the right job. Simple answer, D, direct expansion. For loops, all of that stuff is just to give you a little bit of background for how to think about that. Yeah, so we did get a very brave Megan sent in her answers to the exam, and sure enough, Megan got it right. Direct expansion for number 3. She got a few right, few wrong. We'll go through a few of those as we go along. Thanks, Megan. All right, number 4. Number 4 is starting to talk about electricity again. Which type of transformer would you expect to see at a generation plant of a utility? Step-down transformer, a step-up transformer, air-cooled transformer, low voltage transformer. Well, we can definitely take low voltage off the list. Low voltage is referring to a type of system that like your alarm systems and your phone systems and things like that. That's a totally different animal. It's different from saying that the voltage is lower, right? You can have a lower voltage, but low voltage means something. So our big question is between A, B, and C, and really C we're not going to really think about either, although that could be a potential answer in the classic way of the exam. That's a reasonable answer, but it's not the most reasonable answer. So the question really is between A and B, is it a step-down transformer or a step-up transformer? This is kind of a terminology thing. It's just you have to get used to the way that they talk about it. The sort of key thing to take away here is that remember volts times amps equals watts. When we make the volts go way, way up, we actually make the amps go way, way down. So when you talk about high voltage systems, that means there's very, very low amps in that. There's this kind of odd relationship here, which is that the square the cross-sectional area of the wires carrying the power, carrying the total watts through that system can be smaller if I have much higher voltages. If I have much lower voltages and therefore higher amps, the cross-sectional area of the wire goes up, is much larger. So you can imagine from a cost standpoint, if this thing is, say, 100 miles from the big city, and I would need to make the wires, 5-6 times the cross-sectional area by keeping it at a low voltage, I'm just not going to do that if I'm a power company. I'm going to jump that voltage up as high as I possibly can in order to make those wires as cheap as reasonably possible, because there's a lot of them and they got to go a long way. So what we're going to do is we're going to step up transform. It's going to be B. There's going to be a transformer right there as the power comes out, as the watts come out of the utility. We're going to step it up to probably a few thousand, might be 10,000, might be 18,000 volts. And it's going to then get sent in those high voltage lines, those big systems. It's going to get sent in the big distances that it needs to go. Then intriguingly, it'll step down when it gets sort of close to its end use. So it steps down to its distribution area. So then it might step down to a few thousand volts or something along those lines. And then as it gets distributed around through what we would think of as telephone poles or underground systems, then it'll get to the actual use point. So say, for example, a little house with the little transformer up on the pole out in back of the house. That's a transformer. That's where it's stepping down from the distribution level of power to the actual use level of power, to sort of the everyday use that we would normally find, either the 120, 240, that kind of range. So it steps up in order to do the big, long distances, and then it steps down to get distributed, and then it steps down again to get used. Now, in actuality, there might be 10 steps up and then 6 steps down. Every situation is going to be different. It depends on how close you are to the power generation. There's a whole series of different issues that are going to happen on here. But the gist of it is you're going to step up for the big distances. You're going to step down for distribution, and then you're going to step down again for actual use. So one little caveat to this that's probably worth remembering is, in this little sketch, I'm showing a little house with a little transformer out back. If you all go home tonight, go look out your apartment or out your outside of your house, you'll see that transformer. They're all right there. If you're doing a high rise, the same issues of higher voltage with lower cost because you want to keep the wires smaller are going to be there for the high rise as well. I have a big distance to go up to, say, a 30th floor or 50th floor of a building. So on bigger buildings, instead of having those transformers outside, I may well have them actually stationed at different points through the building, inside the building, which can cause some interesting issues, right? I now have very high voltages moving through the building. So there's a lot of specialty safety stuff that has to happen, but that's worth doing because it's so much different in cost. You would actually have to have very, very large chunks of copper in order to get the total amount of power needed for those elements. And that's just not reasonable. You want to do it through sort of more simple wires if you can. There's still going to be big wires, but you'd want to do it through wires as much as possible. So they'll run very high voltages and then have transformers at multiple stations throughout a building. So fairly simple and straightforward, but that's like when you hear high voltage power lines, they're much higher up in the air, they're far away from people, they're very dangerous. And then when you get to distribution, you drop it down. When we get to use, you drop it down again. Let's take a look at number 5. So number 5, we're talking about cooling. And one of the things that you will probably already realize is there's a lot of kind of weird archaic terms that get used through these processes. One would be a ton of cooling. Like a ton of cooling is kind of an odd term. Like, the hell does that mean? Like a ton of cooling? Well, so technically, I think originally a ton of cooling is The heat of fusion, so this is when ice turns to water. There's a process that happens, and it's the amount of energy it takes for that process to happen for 1 ton of ice to turn to water. I think it's not even quite technically that. I think it's like there's a short ton and a long ton. There's all these kind of simple technical slight variations. I wouldn't worry about it. The gist of it is there's a ton of ice somewhere. It turns to water. That's the amount of energy. It's completely useless to you because, like, what the hell does that mean? The only thing that's useful for us is that it gives us a way to quantify how big a cooling load that we're going to use for our systems. An actual number that's probably worth remembering is that a ton of cooling is equal to 12,000 BTUh. That's one that just might show up. It's probably worth remembering that one. So the question actually is, which range is most reasonable for estimating cooling loads for buildings located in the continental US? A, 200 square feet per ton to 600 square feet per ton. B, 500 to 1,000. C, 12,000 to 24,000. D, 100 square feet per ton to 200 square feet per ton. So this is really just seeing if you kind of know the general range of how much cooling generally happens in a typical building. If you haven't dealt with this kind of system, you probably haven't come across it before. You haven't probably thought about it in this way. This is just one of those numbers. It's worth kind of remembering. The number that I always use is about 300 square feet per ton of cooling. So the range A is the right answer. The range would be 200 to 600. So you might think that's kind of a big range. What's up with that, right? Well, if you start thinking about it, let's say we're talking about a 1,000 square feet of space, and it's just like a house, like a simple, straightforward house, small house. Well, there's not a lot of people in there, right? There's not a lot of activities. This is showers and cooking and people walking around stuff, but it's not a big number of people, right? So I'm not going to have a giant I'm not going to have a giant cooling load generated by the number of people. And let's say there's a lot of trees, and so I get pretty good shade. So I'm not going to have a giant cooling load generated by solar radiation, right? Okay, so I could probably go up to the upper end of this range and say, so 600 square feet per ton, 1,000 square feet. So it's 1.5 tons to 2 tons, somewhere in that range. That's going to be plenty for that. All right, let's say that same 1,000 square feet is a seminar space, and sometimes that thing has 80 people in it. Well, that's going to be a totally different cooling load, right? And I would definitely go way down towards the 200 square feet. So that would end up being, say, 5 tons of cooling. So the same square footage, right, but different use, different cooling needs, I would then sort of range it back and forth within that range. So there's nothing sacred about these numbers. They're just sort of the general kind of rule of thumb numbers that most people would kind of have at their fingertips when they talk about these things. I always just remember 300 personally, and I just use that and then let some engineer figure it out for me. But that always gets me in the ballpark. But, the 200 to 600, you can kind of see how you could kind of adjust it to the situation. So again, the ton of cooling is left over. That terminology is left over from back in the early days of figuring all this stuff out, and that's how they actually figured it out. Was they related it to things they could measure, and one of them would be how long it takes, the amount of energy that you get from the process of ice becoming water. Let's look at number 6. So number 6 is kind of ridiculous. Number 6 is about the vignettes, really. So what we're talking about here is the light levels from different fixtures and how you figure out how many lights you actually need in a space. The light levels in actuality, if you were doing a true sort of really accurate version, this would not be the way that you would do it. This is actually a fairly simplistic version of how to think about these things, but it's sort of useful and fast. And this is the one that's on the vignette. So this is the one you have to get used to using, this sort of terminology. So, okay, using the charts on the last page, what is the space? What spacing would be appropriate for fluorescent 2x4 fixtures for typical 9-foot office space to where the owner desires to have 70-foot candles? So first of all, 70-foot candles these days is actually relatively high. Back in the old days when I was in school, you often would see 100-foot candles, 80-foot candles, but now everything's so computerized that much light actually causes some glare problems. But you kind of get the idea. These numbers will be ranging somewhere between 30 and 70 is probably the highest you'd really go for a typical office these days. So okay, first question is, we have a 9-foot ceiling. We have the 2x4, we have this chart. It's asked for 70-foot candles. Where do we want the 70-foot candles? So think about that for a second. The answer is we want it on the work plane. Well, where's the work plane? Well, it's an office. The work plane is the desk. So if you think about it as either 30 inches or 36 inches, somewhere in that range, kind of gets you right in the ballpark. So that means 30 to 36 inches off of the floor is our work plane. So if we look at the little chart off to the side, you can see that from the ceiling, we have 0 feet to 2 feet to 4 feet to 6 feet to 8 feet to 10 feet. Well, so our floor is right there at 9 feet, but our work plane is going to be at 6 feet from the ceiling. So the thing we care about in this context is the work plane. So we're coming 6 feet down from the ceiling. We'd actually, if we're getting really technical about it, we'd actually go 6'6", probably use 30-inch, but you get the ideas. I'm trying to keep it simple with these charts. So we're at 6 feet off of the ceiling. And then the other thing we were looking at was the 70-foot candles. There's 70. The ones that we have called out are 30, 70, and 90. So we can follow that plume of light that is shaped by this sort of diagram. It's talking about sort of plume of light that comes out that within that volume, the light is at 70-foot candles. And so we look at that 70-foot candles and where it intersects with the 6 feet down from the ceiling, and we are 2 feet away from the edge of the light fixture. Hope everybody can see that. 2 feet away from the edge of the light fixture. And our intrepid Megan, who sent in her answers, you got snookered by that one because you answered 2 feet. Which is a totally reasonable, logical answer, except that you forget you now have to have the other light, because you're talking about the spacing. So I have another light next to it. That light is going to be over here. It would also have 2 feet, where it would cover that 70-foot candles. I put the two of them together. They're 4 feet apart from each other. So a couple things to say about these things. One is foot candles. Foot candles is sort of the most useful term that we kind of run into on these. Lumens is the amount of light leaving a light fixture, but the average architect really doesn't care about that. A light designer cares about it. A product designer cares about it, but the architects, you don't really care about lumens. What you care about is how much light hits the work plane. That's the only thing you really care about. So if I take that same light fixture and I put it up 15 feet higher, I'm going to have, even though it has the same number of lumens coming out of it, I'm going to have way fewer foot candles on the desk. So foot candles are lumens per square foot of area. So that's one thing to say. The other one is really that kind of idea of the work plane. So in this case, it's 2 feet over, but that actually means 4 feet to where the next light would start. This is something you'll have to do on the vignette. So you're going to get used to it. If you were actually doing a real calculation, you'd be thinking about the color of the wall. You'd be thinking about the color of the ceiling. You'd be thinking about how often the light bulbs are replaced. You'd be thinking about a whole series of other issues. There's a great set of examples shown in the MEEB book called the zonal cavity method that kind of goes through all of the different issues. I wouldn't worry about trying to do the zonal cavity method because it's kind of a big, long process. But you can see all the different parts that fit into it. That's when you do one of those ones like an online calculator, or you do something with Rhino or SketchUp or something. It's actually doing that system, and so you can start to understand what your programs are doing for you by looking at that example. Okay, so let's look at the next example, which is another one of these. This is actually a can light, and we're looking for, in this case, using the charts on the last page. So when we sent it out, it was on the last page. What would be the proper spacing for 10-foot lobby to have 30-foot candles using the recessed incandescent can lights? This is 10-foot lobby. So what's the work plane? Is it the 30-inch or 36-inch? Well, no, we're in the lobby. So the work plane now is actually the floor. It's kind of the interesting idea, right? There is no desk in the lobby. I mean, there might be a reception desk or something, but that's a separate idea. The work plane is the floor. So now when we look at this one, we have to look at the full 10 feet from the ceiling. So we're looking at that. We have 40 and we have 25. Kind of do a little interpolation about a third of the way between there. You kind of follow that same curve and go up to 10. And sure enough, we have 4 feet away from the center line of that light fixture. So these can lights, because of the same issue, I'm going to have the same one again on the other side, would be at 8 feet. 4 feet plus 4 feet, it's going to be 8 feet. So this is one of those little tricky ones on that vignette. People make this mistake all the time. They look up these things, they think about it from one, and they put it at half of the distance. You have to remember there's 2 of them, so you don't get screwed up on that. All right, let's move on. Here's a couple that kind of go together. Number 8, what test is typically done prior to sizing of a leaching field? Is it a soil compaction test? Is it a fixture pressure test, a water hardness test, or a percolation test? I'm going to read the next one as well. Liquefied sewage that flows from a building's disposal system into a private on-site filtration system is called leach, effluent, soil, scum. So these are both related to septic systems. And there's a few of these terms will show up in different, not just septic systems, but the way this is described is talking about septic systems. So that's when we don't have a direct connection to, there's no sewer in the street. We can't connect and just dump our sewage off to a municipal system. We have to deal with it on site in some way. So this is not an urban situation. This is some sort of either rural, sometimes suburban, where you have to deal with it on site. A couple of issues about that. Start thinking about, well, kind of, I'm an architect, I don't really care about that. Like, I'll let somebody else figure it out. Well, you better care about it, because you can't put the house or the building just anywhere on the site. Everything has to flow by gravity, right? So the high point, it wants to flow away from. You don't want to have your leaching field flow back into your house. That would be a bad idea. So it does actually have pretty dramatic impact on site planning. It has dramatic impact on access points, because I also need to be able to get a truck there to be able to clean out that septic system every once in a while. So what are we talking about? Let's go back to number 8. What test are we going to do for the field? We're going to do D, a percolation test, because what is going to happen here is I'm going to have the sewage from the house is going to go out from this house. I'm using a house just as an example. It could be other systems, but it's going to go out from this house, and it's going to go to this great big box. And this big box is going to then have the sewage come into it. And it's going to sort of drip into it. And then it's going to, and we're all adults here, right? You have to kind of get by all the grossness of all this stuff. Well, some of us are adults, I guess, but maybe not Mark. I'm not sure. But as that sewage goes into the septic sort of box, it actually separates. And I start getting solids that drop to the bottom of the box. And then I have the effluent, which would be the answer to number 9, is the sort of liquid portion. And then I have scum that rides on the top. It's a great term, I think. I love it. It's so straightforward. Scum rides on the top. So it separates itself out. Now, why do we care about that? Well, the reason we care about it is because the solids we're not going to do anything with. We're going to let that build up in that box. And so therefore it has to get, every once in a while, somebody's got to come out and actually take a great big, really horrible vacuum and put it down into that box and pull it all out so we can make it fresh again and go. So when you see these systems, they have to be maintainable. The effluent, however, we can deal with. And what we deal with it is this very high-tech system where you put it into a pipe, that pipe has holes in it, and the effluent goes out into the leach field, which is a bunch of sand. and it drains out into the sand, and that's about as high tech as it gets. So sand is how we filter the sewage. Now that sounds a little weird. You're like, well, really, that's enough? Well, sand is actually how we filter sewage even on big urban systems. It's the same system. It's just we're using the sand that's in the field right there instead of in a sewage treatment plant. So a couple things to think about there. Well, what if we had clay? Could we do this in clay? Absolutely not, right? It's not going to be able to leave that pipe. It's going to back right up. It just wouldn't work. Could we do it in gravel? No, the trouble with gravel is it's going to flow too quickly through that soil. And so you're not going to get the cleaning aspect of it. It's not going to work, right? Sand is what it's going to be. There's a lot of variants of the sand. It can be a little bit silty. It could be a little bit of this. It could be a little bit of that, but it's going to be sand, right? So that's what the percolation test is about, is finding the right level of percolation. It's going to go through that system easily, but not too easily. And the effluent is going to be that liquid portion. How's that for some excitement? Tell your friends all about that. Okay, which of the following statements about forced air, this is number 10, forced air heating system is not true. Forced air heating systems can be augmented with humidification. Gas-fired forced air heating excels at temperature modulation. Air pressure is measured typically, weirdly written, in inches of water. Or D, forced air offers the lowest capacity of heat per unit volume. So first thing to say is absolutely air offers the lowest capacity of heat per unit volume. This is sort of obvious once you start to think about it. I have great big ducts that move conditioned air around, but I have little tiny pipes that move hot or cold water around, right? That's what D is saying, right? It takes a lot of air. It doesn't hold the heat or the cool in the same way. It takes a lot more. So D is true, therefore it's not the correct answer. C, how about air pressure is measured with inches of water? Yeah, it's another one of those kind of archaic terms. It's a way of discussing pressure. And it has to do with the pressure lifts water a certain number of inches in a set. Doesn't really matter. Inches of water is how pressure is described in those situations. So C is also true. Therefore, it's not the correct answer. So it's between A and B. And one of the things we can definitely say about the great thing about air-based systems as opposed to hydronic water-based systems is that it's really easy to just add a little bit of moisture if you want to add humidification. The other thing that's great about air-based systems is that the sheer fact of air conditioning removes water out when there's too much moisture in the air. So humidification is something I can definitely deal with very easily with air-based systems, which leaves us with B, gas-fired forced air heating excels at temperature modulation. If you think about this, if you've lived with this at all, you know this isn't true. So therefore, it's the correct answer because that heating system kicks on and it's really loud and then it kicks off. And then it kicks on again and it's really loud and then it kicks off. That's because it can't modulate. It's either on or it's off. There are versions of air-based systems that can do this, but they're way more complicated specific systems. All right, let's keep moving. It's another kind of fast one. How many BTUs does it take? This is number 11. How many BTUs does it take to raise a cubic foot of water 5 degrees Fahrenheit? A cubic foot of water is 7.48 gallons. A cubic foot of water weighs 64 pounds. This is one of those kind of odd, archaic pieces again that is sort of part of the everyday life of the various engineers who work in these. The 7.48 gallons is not meaningful to us. That's a red herring, just as there to throw you off. The one key thing is the 64 pounds for a cubic foot of water, because one term that you should kind of generally know is that a BTU is actually defined as the amount of energy it takes to take 1 pound of water 1 degree Fahrenheit. So a BTU, that's what a BTU is. It's the amount of energy it takes to move 1 pound of water 1 degree Fahrenheit. So we've got 64 pounds. We're trying to move it 5 degrees. You multiply 5 times 64, you got 320. A is the answer. Another fast one, 12. Which of the following is not a type of electrical raceway? It's kind of a technical term, raceway. When I think of a raceway, I think of the big trays in like large commercial settings. But a raceway is actually any time I have a carrier for wires. So conduit is actually a raceway. EMT is a conduit. It's thin wall conduit. IMC is also a conduit. It's a little bit thicker and it's actually threaded. There's a couple. There's like a rigid conduit. There's like another was a watertight conduit. There's a couple different ones, but EMT and IMC are both very typical that you find often. And then greenfield is actually a flexible conduit. The place that most of you probably see that is when you do a whip. Say you're going from a junction box in a wall up to how about a fan hood above a stove, right? You don't plug the fan hood in; it gets directly wired. Well, and that often happens kind of down the road in the construction process. So exactly where that thing is going to be, it's always a little hard to call. So they put a whip in. So that's a flexible piece of conduit, which would be the flexible metal conduit, which is typically referred to as greenfield. Although that's, I believe, a product name. So the actual answer is BX. BX is the type of wiring that comes with a sheath around it already when you buy it. So you can't pull the wires out and rewire it. That's what a conduit, a Raceway can do. A Raceway, I can always take the wires away and put new wires in. BX is already wired, and so that would be an example that is not a Raceway. Romex would be another example like that. Another quick one. Which of the following is the method for rating transmission of sound through doors? It's number 13. And the answer to that one is C, STC, the sound transmission. And I always forget whether it's coefficient or class. Coefficient? God, it always throws me off. So the STC. So that's talking about transmission, right? So that's through things. Right, it's different from the ratings that we would do for ceiling panels or something where we're looking at noise reduction. It's different than other ways that we would talk about sound. This is talking about sound moving through things. So wall assemblies have STC ratings, doors, windows, they all have STC ratings. It's how you can define, is the use of this one space going to work next to this other space, or is too much sound going to go through that wall assembly, through that door, through that window, and bother the neighbors, right? So STC, it's a key one for keeping your tenants happy. So that's one you want to definitely know how to use. And then last but not least, this is a really good word for you to know. It's enthalpy, because it sounds so weird. It's really easy to ask a question on, and it's actually a fairly simple, basic concept. When we deal with heating and cooling, specifically cooling, we're talking about comfort. And we talk about comfort, we're talking about two different issues. You're talking about temperature and you're talking about humidity level, right? Both of those, you can't talk about comfort and not talk about both, right? We've all been in the situation where you've been somewhere and it was 90 degrees, but relatively low humidity and it felt fine. And you've been somewhere else where it was, say, 82 degrees, but really, really high humidity and it felt horrible. Right? It's not just temperature, it's the combination of the two of them. When we talk about temperature on a thermometer, we're talking about what's referred to as sensible temperature. That's something that we can look at on a thermometer and it goes 10 degrees higher. It's very straightforward. That's a sensible temperature. That's a thermometer-based way of looking at it. Latent heat is a different concept. Latent heat is dealing with the moisture levels. So, for example, if I'm boiling water, let's say you're making spaghetti, you put the big pot of water on the stove, and I'm heating that up. I have the flames are on, and it's making it really hot. As that thing heats up, as it gets hotter and hotter, right? Eventually, it starts to boil. Like that energy is going into it, and it's making that water hotter and hotter, and now it's boiling. Well, it's still boiling, right? The water is actually still at 212 degrees, roughly. It actually goes up a little bit, but it's still boiling, but the heat is still on underneath it. So where's all that heat going? Well, this is the kind of issue. It's going through that process of the transformation from water to steam is able to accept an enormous amount of energy in that process. So we use that for moving heat and cool around all the time. This is a related issue to the refrigerant loop. So the concept of enthalpy is that it's the total heat. So this means if I need to move the temperature of the office space from 82 down to 75, but I also need to move the moisture level in that office space from, say, 76% relative humidity to 53% relative humidity. I have to do both of those things. Those are two. One I can do by changing the sensible temperature through cooling. The other one I have to do by removing moisture, and that there's an energy it takes to do that, and it's how I feel comfortable in that space. The energy it takes to do both of those things would be the enthalpy. It's a way of looking at both elements together in one number. And there you go. It's a really good one to know. We also had one question that was asked earlier, which I'll just do a quick thing. I just call it the idea of a heat sink. Heat sink is a very simple concept. I'll give you a quick example. I was just working with some folks doing a large greenhouse, and they have some great big barrels. They filled those barrels with water, and you kind of think, well, what are they doing with that water? In the greenhouse, as the sun warms through the glass and warms up the barrels take in a huge amount of heat, and then they are slow to give it off over a long time over the night. It's a big heat sink. It has a huge capacity for heat. Other materials won't have that capacity. There's lots of materials you can think of that they would get hot in the sun, and then as soon as the sun's gone, they're not warm anymore. Well, that water will modulate the temperature in a cold night for that greenhouse. That would be an example of a heat sink. The other sort of classic examples, we happen to be here in Chicago. Chicago has, anybody who's been around here has heard cooler by the lake. The idea that the lake has such a huge impact on the temperature when you're near it, that's because there's a huge heat sink in the lake, and it absorbs this massive amount of heat, and so it modulates the temperature in a different way. This gets used in all kinds of different ways. You'll see it used at very small levels for keeping computer systems, servers, and things like that cool. You'll see it like in greenhouses. You'll see it in just sort of understanding climate. There's all kinds of ways that the idea of heat sink shows up. It's a fairly loose term, but that's sort of one of the things to kind of be aware of. All right. Any other quick questions? We're kind of running a little long. Any questions? Absolutely. So like trom walls, things like that, where big, massive concrete. You'll see people will use those as heat sinks. A classic example is like a big glass wall facing to the south with a concrete pad on the inside in front of it. That sun warms up that concrete pad. And therefore, at night, when it gets cold outside, the concrete is holding on to that heat, and it's eventually giving it all off over the night. But like trom walls, concrete, big masonry structures, things like that. But something like if you did that with a wood floor, it wouldn't work because it's not a heat sink.
Did have a couple questions just confirming the answers to number 2 and number 9.
Okay.
So let's see. Number 9 was effluent.
Effluent.
Right?
Number 9, the answer is effluent, and that's the fluid aspect to the sewage. And it's important to us because we can deal with it. That's how we get that out to the leach field, and it can drain through the leach field and clean itself off before it gets to the water table. Whereas the solids, we just got to house there in our septic system until we can get somebody to come and take it away.
The answer for number 2.
And then the answer for number 2 is B. The duct system will be sized for the cooling mode because that's the one that is the hardest to meet.
And let's see. Also 14. Let's see.
Because I didn't actually
enthalpy.
answer these. I didn't ever actually answer number 14. So it's the sum of the latent and sensible heat. Because the sensible heat is what we can be measured. The latent heat is having to do with the moisture levels, and the enthalpy is the sum of those two together.
And then Stacy had a question. Stacy Kidd Online asked, you always design for the lower delta. That was an older question. I'm not quite sure.
Yeah, that's just referring. You don't always design for the lower delta. It just when the degree days are similar. That's what's going to drive the decision. If you're worried about both heating and cooling, like for example Chicago or any other sort of temperate zone in the United States, then you're going to you're going to choose the lower delta because that's the one that's going to take more air volume to answer the issue.
And then Stacy's asking, how is cooling load hardest to meet when the winter temperature differential is greater?
The temperature differential is greater, but not in terms of the outside, but not the temperature differential inside the space. Once you've heated the space up to a certain degree, what you're talking about is modulating the temperature from that point. So yeah, it's a really good question. Sorry, I should have been more clear about that. What you're talking about there is modulating the indoor temperature. So if it's say 65 inside and you want to raise it up to 69 degrees or 70 degrees, that's what we're talking about. We're trying to deal with that part. We're not necessarily trying to deal with the outside air temperature. That's a different set of questions that starts to come up with, like, well, what's the R value like in the wall, and there's a whole other set of issues that would regulate that question. The way that so the question was, if air-based systems are great with humidification, either taking dehumidifying or humidifying, how about hydronic systems? Can hydronic systems be useful in that way? And the answer is there's a couple of very specific small scale versions where yes, that it can be used, but essentially no. The sort of general, most of the time answer would be hydronic systems do almost nothing for you from a humidification standpoint. So what you end up having to do is have a humidifier or have a dehumidifier, right? That you have to add separate systems that allow the humidification issues to happen, but it doesn't happen naturally. One of the cool things about air conditioning systems is that when you make the cool, which is a weird thing to say, but when you make the cool, the air around that refrigerant gets cooler, and therefore it can't hold as much moisture in the air because warmer air can hold a lot more moisture. So when you make that air cooler, that cooler air drops away. There's condensation. It drops away a bunch of the water that's in the air. So air conditioning naturally dehumidifies, which is a very handy thing. That's part of that latent enthalpy kind of whole discussion. If you've ever put in a window air conditioner and accidentally not tilted it to the outside, you've probably seen that your bedroom floor got covered in water. Well, that's what's happening, right? It's pulling moisture out of the air, or it's dripping on you when you walk into the store and it's the air conditioner is above the door, right? It's pulling moisture out of the air from the inside, and then it's just getting rid of it. And a window air conditioner just drips it away. It's sort of simple versions, but other ones have more complicated condensate systems.
We did have one other question. Megan's asking about basically how do you know whether different regions are temperate or not? Where would you go to find out if it's a temperate zone?
Yeah, there's actually all sorts of sources. However, your local code would actually have quite a bit to say about that, because they will have you trying to meet various degree days just sort of locally. So there's probably some place that your local codes reference, and you should use those references if you want to be able to get a permit. But you can actually find it in all sorts of sources. If you look at even in something as simple as graphic standards, there'll be temperate zones shown, humid zones shown in sort of large maps, and you can kind of get a rough justice idea from those. But there's actually a million sources out there. I would start with the simple ones like the graphic standards and the other sort of climate-based versions of those things. But you can find it all over the place if you take a look.
All right, well, thanks, Mike. And thanks to all of you who've tuned in. If you'd like to attend our next ARE live broadcast, visit blackspectacles.com/podcast to register to attend. You'll have a chance to ask questions and share your answers with Mike for live feedback during that broadcast. And to learn more about our AIA ARE prep curriculum, go to blackspectacles.com. We'll also put a link in the show notes. And for those of you who want to get busy preparing for the ARE, you can use a 15% coupon off the first charge of any AIA ARE prep membership with code 52715webinar, which will expire on June 15th. And of course, if you're already an AIA member, you can visit aia.org/ARE prep to get a 30% discount for the entire duration of your AIA ARE prep membership, not just the first charge. This also expires on June 15th. And finally, please leave a comment below the video to let us know what you think and share any suggestions you may have. I promise we'll read every word that you write and use them to tune our next episodes. So thanks for watching.